Good morning, my dear friends. I hope you all are doing great. So, dear friends, today we'll be talking about the standard enthalpies of different types of reactions. So, my dear friends, we'll be talking about enthalpy of combustion, atomization, bond dissociation enthalpies, enthalpy related to solutions, hydration enthalpies, and all those. So, let us start with the first one, which is standard enthalpy of combustion, my dear friends. When we look at the word combustion, you will understand that you are burning a particular substance, my dear friends. So have a look. Standard enthalpy of combustion is defined as enthalpy change. Enthalpy change basically means delta H naught. Yes, and that can be plus or minus. But we know that in combustion reactions, when we burn something, energy is released. So delta H R naught has to be minus exothermic. That is quite cool. If you burn liquefied petroleum gas, energy is released. If you burn the glucose in the cells, the energy is released. If you burn benzene, energy is released. If you burn methane, energy is released. That means these reactions, combustion reactions, will be exothermic reactions, my dear friends. And this enthalpy change has to be negative, my dear friends. This enthalpy change is delta H R naught. It has to be negative. And we know that in place of this R, we are writing C. This C will tell us that it's a combustion reaction, my dear friends. Let's go further. What is the condition here that is important? How many moles of a compound you are burning, my dear friends? You are burning 1 mole of a compound, my dear friends. So when you burn 1 mole of a compound, is completely burnt in presence of oxygen. Oxygen is required for the combustion. Yes or no, my dear friends? So in presence of oxygen, you are burning 1 mole of a compound with all its reactants and products in their standard states. Here the reactants and the products should be in their standard states. And I defined the standard state last time. What is the temperature for the standard state we are taking usually? Yes, the temperature of interest is usually 298 Kelvin. But I also told you that it varies. Yes, the temperature of interest can vary. But here I am keeping it as 298 Kelvin. So this 298 Kelvin here is a constant temperature, and it's my temperature of interest for these combustion reactions. And I am carrying out these processes at 1 bar pressure. So this 1 bar pressure and 298 Kelvin will define the standard states of these reactants and products. So my dear friends, you are burning 1 mole of a substance in the presence of an oxygen, and the reactants and products should be in their standard states, and the amount of energy released during this combustion process will be basically, revealing us that it's an exothermic reaction, my dear friends. Let's take an example. C4H10. This is butane. And remember, this butane is your LPG, liquefied petroleum gas, which we are burning at homes. The gas cylinders do contain LPG, liquefied petroleum gas. And there can be CNG also. Yes, compressed natural gas. So LPG is butane. Compressed natural gas is methane. You can burn methane also. That's also a combustion reaction. So look here, how many moles of butane you are burning here? Here we have 1 mole. So I have here 1 mole of butane. So you are burning 1 mole of butane in presence of oxygen. Yes? And when carbon burns, it gives me carbon dioxide. When hydrogen burns, it gives me water, my dear friends. So this is the combustion reaction in which 1 mole of butane is burnt in presence of oxygen. Yes? And how much of energy is released? This negative sign will tell me that this is the exothermic reaction, my dear friends. So 2658 kilojoules of energy is released when you are burning 1 mole of butane. Now look here, my dear friends, the C6H6 is your benzene. And how many moles of benzene you have here? Only 1 mole. So you have a 1 mole of benzene here. So when you are burning 1 mole of benzene in presence of oxygen, obviously the carbon will change into carbon dioxide, hydrogen will change into water, okay? And finally, how much of energy you are getting when you are burning 1 mole of benzene? You are getting minus 3267 kilojoules per mole. So 1 mole of benzene is giving me this much of energy, 3267 kilojoules. And 1 mole of butane is giving me 2658 kilojoules. Now, when you are burning 1 mole of butane or 1 mole of benzene, who is giving you more energy? Who is releasing more energy? Obviously, the benzene is giving more energy. You look here, 3267. And this is 2658. Why benzene is giving the more energy? Can you tell me? Why benzene is releasing more energy on combustion? The reason is very simple. Look at the carbon content. How much of carbon is here? 6 times. And how much of carbon is here? Only 4. So this substance has more carbon content. Remember, if any substance has more carbon content in it, so on combustion, more and more carbon is there, it will burn and change into carbon dioxide and more amount of energy will be released. Remember that particular point. Then you can carry out combustion of methane, that is compressed natural gas. You can carry out the combustion of glucose molecule. You can carry out the combustion of other alkanes and alkenes, my dear friends. They have a carbon content in them. Okay, what is necessary for the combustion is basically carbon and hydrogen content is necessary. Remember, for combustion process, especially in hydrocarbons, there is carbon and there is hydrogen. These two things are essential for carrying out combustion reactions. So look here, my dear friends, if you CH4 methane is there and carbon dioxide is there. Out of them, who will burn? Who is a combustible substance? This is a combustible substance, my dear friends, because it contains carbon and hydrogen. It contains carbon and hydrogen. But this is basically a fire extinguisher. This is a fire extinguisher. Means it does not burn, but it stops the fire. Carbon dioxide does not burn, but it will stop the burning process of fire. Reason is simple. Carbon dioxide contains only carbon. It does not contain hydrogen. So remember, for combustion process, carbon and hydrogen both are equally important. Yes or no? Look here, carbon and hydrogen is here, so it's a combustible substance, it will burn. But when you look at carbon dioxide, methane is combustible substance because it contains carbon and hydrogen. Once again, I'm telling you. But carbon dioxide is not a combustible substance, it's a fire extinguisher. It will stop the fire because it does not contain the hydrogen content. So greater the carbon and hydrogen content in a molecule, yes or no? Greater is the chance of a combustibility and greater will be the release of energy. Please remember that particular point and make note of this. Dear friends, let us talk about now the second point here, that is standard enthalpy of atomization. And what is this all about? You will take one particular substance, okay, which is made up of many atoms. Then you will just give energy and separate those atoms. The separation of atoms from any given substance, that is basically called as atomization. Let us suppose if you have a methane molecule. How many atoms are there? 5 atoms. If you provide energy and separate all those 5 atoms, that means that is called as atomization, my dear friends. Now look here, you have H2. How many atoms are here? 2 atoms. So if you provide energy and separate these 2 atoms, that will be the atomization. But it's not that much simple, my dear friends. Usually, we will be taking the concept in terms of moles. So let us understand it in terms of moles, but before that, let's understand the definition. Standard enthalpy of atomization is the enthalpy change And here it will be, the enthalpy of atomization will be positive. It is endothermic, my dear friends, remember. Why it's endothermic? Because you are supplying the energy and separating the atoms from a particular molecule. Yes? Okay. That accompanies, look here, total separation. That's important. Total separation of all the atoms. Yes, my dear friends? In a chemical substance. And let us suppose your chemical substance is CH4. So this is your chemical substance, CH4. Then you have to do total separation of all the atoms. That means you have to separate all these atoms. How many atoms are here? 5. 4 hydrogen, 1 carbon. So you are separating them. 1 carbon, and now we have here 4 hydrogen. It has to be like this. It has to be like this, my dear friends. 4 hydrogens we have here. So you have separated them. You have separated all. And how much of energy you have spent here? 1665 kilojoules of energy you have spent, my dear friends, in separating all these atoms. If this is your chemical substance, what you are doing total separation of all the atoms. All the atoms are separated. Carbon is separated, hydrogen is separated. Yes or no? And how much is the enthalpy change during this particular process? That is 1665 kilojoules, my dear friends. So understand, this will be called as the standard enthalpy of atomization. Let us understand it in more detail, my dear friends. Have a look. Now if you take the first example here, H2, you can take it as one molecule also, and you can take it as 1 mole also. But if you look at this term, you will find out that it has to be in terms of moles, not in terms of molecules. For understanding, you can take molecule also, but when we look at the energy which is used here for breaking H2 into 2 atoms of hydrogen, yes, is in moles. That's kilojoule per mole. So 435 kilojoules of energy is required to separate H2 into hydrogen atoms, my dear friends. And it's with respect to per mole. That means this guy is our 1 mole here, my dear friends. So we have 1 mole of H2. Now everybody knows that in this H2 molecule, everybody is aware, in H2 molecule we have a single bond here. If I have a single bond, if I have a one molecule will have one single bond here, my dear friends. One molecule will have one single bond. But we know that we are taking 1 mole of H2. Yes? So that means this single bond is basically how many times? 1 mole times, that is 1 mole here. That means we will have, how many single bonds we will have? If this is 1 mole here, my dear friends, this is mole. Then we will have 6.022 into 10 raised power 23 single bonds in H2. So, in 1 mole, try to understand, here we have 1 mole of H2. So in 1 mole of H2, 1 molecule of H2 has 1 single bond. Yes? 10 molecules will have 10 single bonds. 1 mole will have how many single bonds? 1 mole single bonds. And 1 mole single bond is what? 6.022 into 10 raised power 23 single bonds in H2. So I am going to break these single bonds. Yes? Then only I can tell that I am breaking 1 mole of the bonds. Which bonds? Single bonds. Okay? So when I break these single bonds, my dear friends, okay, this 1 mole of single bonds is broken by supplying 435 kilojoules of energy, by supplying 435 kilojoules of energy. Okay, so my dear friends, we have 1 mole of H2. 1 mole of H2 contains how many single bonds? 6.022 into 10 raised to power 23 single bonds. Now this 1 mole of single bonds is broken by supplying this much of energy. Okay, now finally what we have? Finally we have, how many moles are here, my dear friend? These are 2 moles. These are 2 moles of hydrogen atoms. It's a 1 mole of hydrogen H2 molecules, and 1 mole of H2 molecules gives me 2 moles of hydrogen atoms. So these are the 2 moles of hydrogen atoms. So finally we have 2 moles of hydrogen atoms, and this is very much important. They have to be in the gaseous state. Obviously the 2 moles of hydrogen atoms will be in gaseous state. How come they will be in gaseous state? Because when they were bonded to each other, when 2 hydrogen atoms were bonded to each other, yes, okay, that time also they were in gaseous state. After separation also they are in gaseous state. If they were bonded and they were in solid state, but after the separation they will be in gaseous state. So finally they have to be in the gaseous state. If you look in all these reactions, you will find out the products are in gaseous state. Here also you will see the product is in the gaseous state. Now you understood, my dear friends, that we are separating the atoms. Okay, now in this 1 mole of hydrogen molecules, okay, you will see that we have 6.022 into 10 raised to power 23 single bonds, okay, in H2 molecules, and you have broken all those single bonds, and finally we have 2 moles of hydrogen atoms in gaseous state. So 2 moles of hydrogen atoms we have in the gaseous state, my dear friends. Now you will be thinking that, sir, we are breaking the bonds, correct? So when you are breaking the bonds, obviously this standard enthalpy of atomization can be also called as standard bond dissociation enthalpy. So you can just relate it to the dissociation enthalpy also. Standard bond dissociation enthalpy, because you are breaking the bonds. But why we call it as standard enthalpy of atomization? Because you are separating 2 hydrogen atoms which are bonded through a single bond. You are separating them up and changing them into the atomic form, and that atomic form is in the gaseous state, my dear friends. So that's why we call it as standard enthalpy of atomization. But you are breaking the bonds also. So when you are breaking the bonds also, that means here we will write down delta H A naught, that is the standard enthalpy of atomization. It's also equal to delta H naught bond dissociation, we can say. Let's call it as, okay, dissociation. DISS, dissociation. Because you are breaking the bonds here. And the value is 435 kilojoules of energy is required to break 1 mole of single bonds in 1 mole of hydrogen molecules, my dear friends. Now let's take on the second example here. When we look at now methane, my dear friends, in methane, have a look. Methane is already in a gaseous state. So, if I take 1 mole of methane, 1 mole of CH4 molecules if I take, correct? So, try to understand. If I take 1 molecule of methane, 1 molecule of methane will have how many bonds? 1, 2, 3 and 4 bonds, A, B, C and D. 1 molecule will have 4 bonds. 10 molecules will have 40 bonds. Yes, I know. Or in simple words I will tell, 1 molecule has 4 bonds. Then 1 mole will have how many bonds? 4 moles of bonds. So in this case, we will have 4 moles of the bonds, my dear friends, in case of methane, in case of 1 mole of methane. 1 molecule of methane has how many bonds? 4 bonds. Then 1 mole of methane will have how many bonds? 4 moles of single bonds. So you have to break all these 4 moles of single bonds. This and this. So here, my dear friends, we have to break 4 moles of single bonds in methane. So I have 1 mole of methane molecules. Every molecule has 4 bonds. So 1 mole of methane molecules will have 4 moles of, single bonds. Here we have 4 moles of single bonds. 4 moles of single bonds, which are A, B, C and D. Correct? We have to break 4 moles of single bonds in methane. When we break 4 moles of single bonds in methane, how much energy is required? Okay, 1665 kilojoules per mole. That means we have to break 4 moles of single bonds in methane. We require this much of energy. And finally, what will happen? This methane will separate into atoms. Because that is our topic, total separation of all the atoms from a molecule. So from methane, we will separate all the atoms. We have separated carbon, we have separated 4 hydrogens. And they are in the gaseous state, my dear friends. I hope you have understood, my dear friends. So we are applying the energy. We are separating the, atoms from a molecule or from 1 mole of a molecule into what? Constant atoms in gaseous state, my dear friends. Now the last point is about sodium. So I would like to discuss this thing. Have some patience. Just a minute. Let me erase this thing. Here also, my dear friends, you can tell that this delta H A naught is basically delta H naught dissociation, because here also you are breaking the bonds. So here standard enthalpy of atomization is equal to standard enthalpy of bond dissociation, because we are breaking the bonds. Now let's look at the final example. Here the sodium is basically in solid state. I will take 1 mole. So I took 1 mole of sodium solid. And now you will be thinking, in sodium solid, what I am breaking? What I am going to break in sodium solid? You will be thinking that no bond is there. But remember, this sodium is a metal. And in metals, remember, there is a metallic bond. So metallic bonds are there. So here you have to break. So we have to break metallic bonds in 1 mole of sodium. Sodium solid. So my dear friends, you will be thinking in sodium solid, what kind of bonds are there? Here in case of, H2 was there. There was single bond like sigma bond was there. In case of methane, there were 4 sigma bonds. Okay? But in sodium, what is there? Sodium is basically a metal. There is a metallic bonds are there. And we have to break metallic bonds in 1 mole of sodium. When we break the metallic bonds in 1 mole of sodium, it's just like this, we'll represent it. Let's suppose we have metallic bonds like this in sodium. Just for understanding, I am writing it like this. Let's suppose we have metallic bonds. So we have to break all those bonds in sodium solid. And then finally, the sodium solid will change into sodium gas. That means in sodium gas, what will happen? You will be having sodium atoms like this. Sodium gas, sodium gas, sodium gas, sodium gas, like this. So it's also 1 mole. So here between sodium atoms there was a metallic bond. And you have broken the metallic bonds in the sodium, which was in solid state. Okay, sodium solid state is a metal, there are metallic bonds, and you have broken all those metallic bonds by providing this much of energy. How much of energy? 108.4 kilojoules you have provided. And you have broken all those metallic bonds. After breaking all the metallic bonds, what will happen? Sodium atoms will be now in gaseous state. From solid to gaseous. Now there is no metallic bond between the sodium atoms. They are separated from each other. So you have separated the sodium atoms In which form? Solid form. You have broken all the metallic bonds. Now you got the sodium in the gaseous state, my dear friends. So overall, I must tell you how much of energy is required here. 108.4 kilojoules. And here this is the standard enthalpy of atomization. Here this standard enthalpy of atomization can be related to this standard enthalpy of atomization here can be related to sublimation also. This term delta H naught A can be related to delta H SUB naught, that is sublimation. Why? Because you are changing solid. You are changing solid into gas. So when you change solid into gas, that is obviously the sublimation. So here standard enthalpy of atomization for this reaction is equal to standard enthalpy of sublimation, because you are converting solid into gas. And it's also called as standard enthalpy of atomization because here the atoms are having which bond between them? Metallic bond. Then you are supplying 108.4 kilojoules of energy and you are breaking all the bonds in 1 mole of sodium solid. And finally you are getting 1 mole of sodium in gaseous. So finally you are getting 1 mole of gaseous sodium atoms. So somewhere you have seen that delta H A naught was related to the delta H dissociation naught. That means the standard enthalpy of atomization was related to the bond dissociation enthalpy, and here the standard, you know what, enthalpy of atomization is related to the standard enthalpy of sublimation also, because solid is changing into the gaseous state. I hope, my dear friends, you have understood this concept as well. Okay, please make note of this. So dear friends, now we'll be talking about the standard bond enthalpy, that is delta H naught bond, that is standard bond enthalpy, my dear friends. Now if you look at this, it has two subtypes. It can be yours a standard bond dissociation enthalpy, okay, or it can be a standard bond formation enthalpy, my dear friends. Now when we look at standard bond dissociation enthalpy, that means you have to break something. So what you are going to break, my dear friends, it's related to breaking off 1 mole of covalent bonds, my dear friends. You are breaking 1 mole of covalent bonds, correct, of a gaseous covalent compound. Let us suppose for this particular thing, I will explain you there, right out there. Let us look at now standard bond formation enthalpy. Here related to formation of 1 mole of covalent bonds. Okay, now they are exactly two opposite terms. When we look at dissociation, 1 mole of covalent bond is broken, and when we look at the standard bond formation enthalpy, 1 mole of covalent bonds are formed. So now let us look at their, you know what, relationship. Have a look, my dear friends. If I look at A and B, these are two elements which are bonded together. Okay, so there is a covalent bond between them. Let's write down A and A also, does not matter. Yes, two similar atoms are bonded to each other. Let's put it's a 1 mole. So if it is a 1 mole, that means I have to break this 1 mole of what? Covalent bonds. If this substance is here, 1 mole of A2 in gaseous state, let us suppose it is. So you are breaking not 1 bond, you are breaking 1 mole of single bonds, correct? Or even you can break, let us suppose there is a double bond here. You can also break 1 mole of double bonds. So here we have 1 mole of B2 in gaseous state. Let's suppose we have C and there is a triple bond between them. Okay? Now here we have 1 mole of C2 in gaseous state, and here you are breaking, my dear friends, 1 mole of triple bonds. So in first case you are breaking here 1 mole of single bonds. Single bonds are broken. I can call this line as fission. Which fission is this? It's a bond fission. Fission means breakdown. So here you are breaking 1 mole of single bonds. Here you are breaking 1 mole of double bonds. And here you are breaking 1 mole of triple bonds. In place of this A and A, you can take an example of H2. In place of B and B, you can take an example of O2. In place of C and C, you can take an example of N2. So here you are breaking 1 mole of single bonds, 1 mole of double bonds, and 1 mole of triple bonds. Okay, are broken. So are broken. Yes. So whether you are breaking 1 mole of single bond, 1 mole of double bond, or 1 mole of triple bond, in all the cases, my dear friends, you require energy. So here, delta H, okay, not for the dissociation. You are breaking the bond, my dear friends. So obviously, you should write down here it is positive. So these breaking of bonds is basically an endothermic reaction, my dear friends. That means energy is required to break the bonds. So 1 mole of single bonds are broken, okay, and require energy, and that is positive. For this also, delta H dissociation, bond dissociation will be positive. Yes or no? And for this also, delta H dissociation will be positive. So all are endothermic reactions because you are breaking 1 mole of covalent bonds. So my dear friends, here delta H dissociation will be obviously positive. So dissociation is an endothermic process. And when we look at the relation with respect to the formation of 1 mole of a covalent bonds, it is basically a standard bond formation enthalpy. It is exactly opposite of dissociation. Formation is exactly opposite of dissociation. So I told you last time, if you remember, okay, I told you that the formation, okay, if I tell you that formation, or we can say bond formation, is exactly reverse of dissociation. And if you remember, I told you one thing in previous class, that if two reactions or if any reaction is basically reversed, yes or no, formation of ammonia, if you remember, forward process for the formation of ammonia was exothermic and backward was basically what? Dissociation. So that was endothermic. So delta H sign will change, my dear friends. So remember, if you look at this point, bond formation is exactly reverse of dissociation. So enthalpy signs, standard enthalpy sign will be reversed. Yes or no, my dear friends? That means for this guy, for the formation, let us suppose this is the formation of the bond, okay, delta H, it's for the bond formation, correct? So this will be, my dear friends, negative, that is exothermic. Remember, dissociation is opposite of, you know what, formation. Yes, here you are breaking 1 mole of covalent bonds and here you are making 1 mole of covalent bonds. In all these cases, when you are breaking 1 mole of single bond, 1 mole of double bond, 1 mole of triple bond, so energy was required. So positive, endo. And you know that you are breaking the bonds. And what is the opposite of breaking of bonds? Formation of bonds. That's why I told you bond formation is exactly reverse of dissociation. Which dissociation? Bond dissociation. So standard enthalpy sign will be reversed. What is the enthalpy sign for the bond dissociation? Positive. And what will be the enthalpy sign for the bond formation? Yes or no? That is negative. So my dear friends, I hope you have understood this terminology here. And now we will mainly focus on here bond dissociation enthalpy. And you know that bond formation enthalpy is exactly reverse. You reverse that reaction and that's exactly the bond formation. Yes or no, my dear friends? Have a look here, I can just show you that as well. Let us suppose you have A and A. I will break this particular bond, then I will get 2 times A in gaseous state. Okay? So this is here we are breaking 1 mole of covalent bonds. Now what is exactly opposite of this? How many times A we have? 2 times, so I will combine A plus A. That means we have 2 times A. I can also write it like this. A plus A, both are gaseous. Let me reverse this reaction. Here we are doing dissociation. So delta H, okay, dissociation will be here what? Positive energy is required. But here we will make 2 elements to combine and they are making a bond, my dear friends. They are making a bond. So here the bond is formed. So enthalpy, standard enthalpy of bond formation will be here negative, it will be exothermic. Here we are breaking the bond and here we are making the bond. Okay? So this is positive and this is negative. So we will focus on the bond dissociation enthalpy here. And one more term is there, that's called as average bond enthalpy. So please make note of this. So dear friends, I told you that the bond dissociation enthalpy or standard bond dissociation enthalpy is exactly opposite of standard bond formation enthalpy. Standard bond dissociation enthalpy is endothermic and standard bond formation enthalpy will be reverse, that is exothermic, my dear friends. So let us study the standard bond dissociation enthalpy and remember opposite of this will be the standard bond formation enthalpy. That is not a big thing, it's a very easy topic, you know. So let us have a look here. The enthalpy change, and we know that this enthalpy change is obviously positive, my dear friends. Yes? When we dissociate the bond, we require energy for breaking the bond. And how many moles of bonds you are breaking? You are breaking 1 mole of covalent bonds. Yes? Of a gaseous covalent compound. So you take a gaseous covalent compound. Let's suppose hydrogen is our gaseous covalent compound. It's a covalent, okay, substance. Okay, my dear friends. So what I'm going to do? To form products in the gas phase. These are my products. These are the products. In which phase they are? They are in the gaseous phase, my dear friends. Now what is the question? I have to break 1 mole of covalent bonds. If you look here, I am mentioning this. This is basically your delta H naught dissociation. And you are breaking actually 1 mole of single bonds, my dear friends. 1 mole of single bonds. In previous time I told you this H2 will be in this form. Yes? So we have 1 mole of H2. So you are breaking here, if this is 1 mole. So we have 1 mole of these bonds. Okay? So we have here 1 mole of single bonds. Because we know that this guy is how much? It's a 1 mole. So here we have 1 mole of single bonds. So this line will indicate the fission process. Fission basically means you are breaking or we are breaking 1 mole of single bonds. 1 mole of single bonds. So look here, my dear friends, you have to break this 1 mole of single bond. It's not a 1 bond. In 1 molecule it's 1 bond, but in 1 mole, this is 1 mole of bonds. So you are breaking actually 1 mole of bonds right out here. And how much energy is required for that? 435 kilojoules per mole. Yes? If you reverse this reaction, it will become the formation. Standard enthalpy of formation. And 435 will become minus 435. Endothermic will become, come on, exothermic. If I reverse it, it will become standard enthalpy of formation. Yes? Now look here, my dear friends. In this entire process, you are breaking 1 mole of single bonds. Now look here in O2. You can see here you have to break 1 mole of double bonds. Here in this case. Let us suppose this is our 1 mole. And in 1 mole we will have these bonds. So we are breaking here. So tell me, we are breaking 1 mole of double bonds are broken. Double bonds are broken, my dear friends. Yes? And during the breaking of 1 mole of double bonds, that means you are basically breaking 6.022 into 10 raised power 23 double bonds are broken. How you can break them? By supplying this much of energy. So if you supply 428 kilojoules of energy, you can break, yes, 6.022 into 10 raised power 23 double bonds. If you supply this much of energy, my dear friends, we can break 1 mole of single bonds. So both are basically endothermic. Now you can break 1 mole of triple bond also here. Yes, here you are breaking 1 mole of single bond, here you are breaking 1 mole of double bond, and here you can break 1 mole of triple bond also. So here you can break 1 mole of triple bond, and obviously here also you require the energy, and representation will be like this for dissociation and triple bond N. So it will be also positive. That means here also energy is required for breaking 1 mole of triple bond. So here we can break 1 mole of triple bonds are broken. Whether you break 1 mole of single bond, 1 mole of double bond, or 1 mole of triple bond, if you look at them, H2, then O2 and N2. Remember, my dear friends, this H2, N2 and O2 are diatomic molecules because there are 2 atoms and 2 atoms here, N2. So that means we are actually learning the standard bond dissociation enthalpy with respect to diatomic molecules. Okay? Standard bond dissociation enthalpy with respect to diatomic molecules. Yes? And what are those diatomic molecules? You can take O2, you can take H2, you can take N2, you can take Cl2, you can take F2, etc. And you can break the bonds in these molecules. And this standard bond dissociation enthalpy is represented like this. In case of hydrogen, H single bond H. In case of oxygen, O double bond. In case of nitrogen, N triple bond. In place of all these, you can mention here delta H dissociation also. Yes, it is your choice how you are representing it. You can write down in full also bond dissociation, or you can mention here bond also. Correct? And remember one more thing. In all these 3, first, second and third reaction, you are basically breaking the bonds and you are separating these nitrogens into atoms. You are separating O and O into atoms. You are separating H and H into atoms. So that means this dissociation enthalpy here can be also taken as is equal to delta H A naught. That is the enthalpy of standard enthalpy of atomization. They are equal. Because you are converting this molecule into atoms, and that is your standard enthalpy of atomization. And here also you are converting this into atoms. So this is also equal to here delta H O double bond O naught is equal to delta H A naught. That is atomization. Here also you are converting a particular molecule into atoms, and that is the definition of atomization also. So here also delta H dissociation you can call it as delta H N triple bond N naught, or you can call it as delta H A naught. So here in these 3 examples, these are diatomic molecules. Yes, the standard enthalpy of dissociation is equal to the standard enthalpy of atomization, because in all these reactions I am converting the particular molecules into what? Atoms, and that is the definition of atomization also. Please remember. And why dissociation? Because I am breaking bonds. Why atomization? Because I am converting molecules into atoms. Once again, Why dissociation? Because I am breaking single bonds, 1 mole of single bond, 1 mole of double bond, 1 mole of triple bond. So dissociation enthalpy, standard dissociation enthalpy. Why the atomization, standard enthalpy of atomization? Because I am converting the molecules into atoms. I am separating them into atoms. That's why standard enthalpy of atomization. Please remember this particular thing. Dear friends, let us talk about the mean bond enthalpy or average bond enthalpy. Let us take one substance with us, that is CH4. CH4 is basically a polyatomic molecule or polyatomic substance, as it contains more than 2 atoms. So it's a polyatomic substance. Now, if we look at this methane closely, have a look here at this point. Here you have 1, 2, 3 and 4 bonds. Let's call them as A, B, C and D. So let us suppose you are breaking this 1 mole of single bond first. Correct? Let us suppose I have 1 mole of methane. Let's suppose this is we have 1 mole of methane. And you are breaking 1 mole of single bonds. 1 mole of single bonds. Let's suppose you are breaking this A. So let me mention this in place of 1, I will mention it as A. So when you are breaking 1 single bond here in 1 molecule, or you are breaking 1 mole of single bonds in 1 mole of methane. Yes? So my dear friends, if this is 1 mole, then you are breaking 1 mole of single bonds here. Which single bonds? A. So when you are breaking 1 mole of single bonds A, okay, then this hydrogen will be separated. So that means this hydrogen will be removed. So you are removing this hydrogen here. And what remains here? CH3 will remain here. So CH3 remains here. And while breaking this 1 mole of single bond A, this much of energy is required. 427 kilojoules of energy is required. Now, what is remaining here? CH3. So let us mention now CH3. So my dear friends, this is our D, B and come on C. Let us break this bond B now. So now I am breaking 1 mole of bond B. Here I was breaking 1 mole of bond A. I was breaking. Here I am breaking 1 mole of bond B. So fission I am doing bond fission. Here also I was doing the bond fission. Fission means breakdown. So after breaking the bond B, how many moles of bond B? 1 mole of bond B I am breaking. So now this hydrogen will be separated. So it is separated. How much energy is required? 439 kilojoules of energy is required for breaking this 1 mole of CH bond. Yes? Now what is remaining here? CH2. Let's take CH2 now. So CH2 is here now. Okay, let me mention this bond actually here. So this is C and this is D. Let us break 1 more mole of, CH bond. I am breaking this CH bond here. So bond fission is happening. Again I am breaking 1 mole of CH bond. Okay. So when I break this CH bond, the hydrogen will be released here. So you will be left with CH only, 1 bond. So how much energy is required for breaking this 1 mole of bond? 452 kilojoules per mole. And finally at the end we have CH. CH, this is the bond D. Let us break 1 mole of bond CH bond D. Bond fission of this 1 mole of a bond. Here it will be left with 1 electron, here it will be left with 2 electrons, and left with 3 electrons, and finally with 4. So you are breaking 1 mole of CH bond, but D. So obviously this will become our B now here, C and finally D. And how much energy is required? 347 kilojoules per mole. My dear friends, if you look at when I was breaking this CH bond A, this much of energy was required, 427 kilojoules. When I was breaking CH bond B, so this much of energy was required. When I was breaking bond CH, that is C, I was requiring this much of energy to break this bond. And finally, in this unstable part CH, I was requiring less energy, 347 kilojoules per mole. If you see everywhere, I am breaking CH bond here, CH bond here, CH bond here, CH bond here. Everywhere I am breaking CH bond. But energy requirement is different. Yes or no? So I will tell that energy requirement for breaking CH bond or CH bonds in CH4 molecule, okay, are different. So every CH bond has a different value of bond dissociation enthalpy. But now I have come with the concept of mean bond enthalpy or average bond enthalpy. Let me calculate an average bond enthalpy value for the CH bond. You know that every CH bond in CH4 molecule, energy requirement for breaking CH bonds in CH4 molecules are different, or CH4 molecules are different. So can I take now the mean bond enthalpy? Mean bond enthalpy. So I'll be talking about here, I want to calculate the average value for breaking CH bond. So how can I do it? It will be equal to the standard sum of the, you know what, bond dissociation enthalpies of all the CH bonds or 4 CH bonds. Okay? It will be equal to sum of the standard bond dissociation enthalpies of all CH bonds in methane divided by total number of bonds. Okay, so this is our expression, my dear friend. I can fill the values into this expression. Have a look. So now I will have delta HCH. I want to calculate, it's basically the average. I want to find out the average bond dissociation enthalpy for CH bond, my dear friends. Or mean bond enthalpy I want to find out. So it will be equal to sum of the standard bond dissociation enthalpies of all CH bonds in CH4. So let us take on the first one. It will be delta H A naught. Then you have here plus delta H B naught plus delta H bond. Okay, C naught plus delta H bond D naught. This bond stands for here bond enthalpy. Remember, bond enthalpy. Okay. Divided by how many bonds are present in the methane molecule. We know the total number of bonds. Okay, in methane. Directly I will write down there are 4 bonds, or you can say 4 moles of bonds are there in 1 mole of methane. So this is my expression. Then I can put those values here. Let's take on the first value. 427, second value is 439, 439, third value is 452, and the fourth value is 347. So these are the 4 bond dissociation enthalpy values of CH bonds in methane. All are different. This is the bond dissociation enthalpy for CH bond A. This is for B, this is for C, this is for bond D. Divided by total number of what? Bonds. So tell me the total number of bonds in CH4 are 4. So now my dear friends, if you take the sum of these energies, you will get it as 1665. So I have already calculated the sum of these is 1665 kilojoules, the sum of all these. Divided by 4, total number of bonds of 4. And finally your value will be 416 kilojoules per mole. So my dear friends, this 416 kilojoules per mole is nothing but the average bond enthalpy of which bond? CH bond in CH4 molecule. Please remember that. So for every CH bond in average we require 416 kilojoules of energy to break it. Yes? So I will tell you, in an average we require 416 kilojoules of energy to break CH bonds in CH4 molecule. Or shall I say 1 mole of CH bonds in CH4 molecule. So my dear friends, in average I require 416 kilojoules of energy to break 1 mole of CH bond in CH4 molecule or molecules. But if you look there, every CH bond has different value of bond dissociation enthalpy. But when I have taken average, now remember every bond in methane in an average requires 416 kilojoules of energy. But individually they require different energy. But in average they require 416 kilojoules of energy. Please remember this. Meet you in the next class. Have a great time. Thank you.